is the second module of our lectures on thermodynamics. In the first module, we looked at several concepts and definitions and the ways of using them. We did that because that's the stepping stone to what we'll do next, which is to look at the laws of thermodynamics. So before we look at the laws of thermodynamics itself, what we will do is we look at conservation of mass, which is a fundamental law that every system has to follow. And in doing so, we will define something called mass flow rate and flow work. We then move on to zeroth law of thermodynamics, and then the first law, and then second law. So that's the plan for today, tomorrow, and day after. We shall look at laws the way they are in the most general sense, which means that these are applicable to all systems, all types of applications, and are very, very general. So it is this that one always has to remember. Applications may add on, applications may change, issues may change, but the laws don't change. They remain the same. So we begin with conservation of mass, and we first look at the concept of mass flow rate. We have seen that there are two types of systems, closed, open, and we can put the third one, isolated. And in closed systems, we said that the mass of the system is constant. So even though the system may change its shape and size, the same molecules are always there in the system. It is the open system where mass can cross the system boundary, and that is where mass flow rate comes in. So very generally, if we say that there is a duct or a pipe in which there is a fluid that is flowing, and it need not be that every element has the same velocity. These are all fluid elements. And like that, we can build a complete thing across the face of this. So this is a two-dimensional area. And we are looking at fluid elements that cross that area. And we ask the question, how can I get across this area, what is the flow rate, that is how many kg per second of the mass of this substance is flowing to. And for that we will use the symbol m with a dot on top. So this symbol will keep coming on later on also when we look at the laws of thermodynamics. Now we will see how to connect it with this. The basic concept is that you take any surface, and I am showing an elemental surface, and there is an elemental fluid element which is crossing this. Then how much mass crossed this surface? That's the question. So we have two issues here. This is the velocity vector of the fluid, and the surface is there, and there would be a normal to that element. And now, wherever we pick this surface, the total flow rate is not affected because the fluid doesn't care which way we choose our surface. So in this problem, if the surface were like this, or like this, or like this, the mass flow rate through this pipe doesn't change. Only our mathematics changes. So what is happening here is that we say that this normal to this elemental area, this is dA times the normal, so that's a vector now. So this we put as dA star. So if you look at the two-dimensional counterpart of this is the surface, this is the element, and it is crossing this. So at some point it begins to cross, then somewhere here it is crossing it, and after some time it has completely crossed this. So after this has crossed, we say how much mass went through this. Now, before we write the formula, let's look at another case, that this surface could be perpendicular to this flow, or the surface is here and this is going this way. If you look at this second case, if we ask how much mass is crossing this surface, it must necessarily be that the mass goes from this side to this side or this side to this side. But if this fluid element is just going across it like this, then there is no mass flow rate across this surface. So if what this happened, because the normal area vector here is here and this velocity vector is here, and we get the dot product of these two, which is 0. So basic idea is that if our surface is such that the velocity vector is along the surface, or always the area vector is normal to the velocity vector, then there is no mass flow rate taking place across the boundary. In this case, the normal vector is here, velocity vector is here, both are collinear, both are in the same direction. So the mass flow rate in this case, if you take the dot product again, it will be just equal to the product of the magnitudes of these two. And in between here, it will be a mixture. This is the dA vector, this is the V vector, and we get the dot product of that. So the fluid did the same thing. It didn't care where the surface was. So if we do that, and this we are doing for one little element over here, then we say that delta m dot, this is equal to V multiplied by dA. And then we say, well, this is what is happening over a small element. I want to know what is happening across the entire cross section of the pipe, which say in this case, we could have taken a cut. It could have been like this, or this could have been like that, or it could have been any other shape. There is no restriction on the type of surface that we are taking up here. And then we say we will do this integration over this entire surface so that the surface is intersecting the boundary of this channel of the pipe. So we then say that this is integrated, and we get this is integral of V dot dA, and so m dot is integral over the surface V dot dA. So that's our starting equation, and in case A is perpendicular to V, then m dot, this has to be a density here, this is rho V into A. Rho is the density, V is the velocity, A is the area, and in doing this integration and getting one V here, we made one assumption that V is uniform over the entire area A. In reality, that may not be the case, but that doesn't matter. At least in this course, for the purpose of calculation, we will say that area is uniform everywhere, and when we say velocity is so many meters per second in a duct or in a pipe, we will implicitly assume that this velocity is applicable over every point in this area. And that's what gives us the flexibility to write m dot as rho v A. A now is the area of this, and it is not this area but the area normal to V. So then we have to look up a cross section of this, which in the case of pipes, A becomes pi into d square by 4, where d is the inside diameter of the pipe. Or if it's a duct, it is the inside dimensions of the duct from where we get this area. So this is the first definition that we looked at. Let's now look at the concept of what happens when a fluid element is pushed into a control volume. So we take a system, and I'll denote the system here. This could be any shape, doesn't matter. That's our system boundary. And say that this system at some point is such that it is connected to a pipe or a duct across whose face we have taken this hypothetical surface. And we say that in this case, whatever fluid is here would be here, and an element of this fluid at some time t1 is just outside this system. So we have two systems. One is this big one, which is our control volume, and the second is this little element of fluid. And what we do for this is, first we say that okay, the area of this is dA, this length dl, the pressure acting on this is P, and its specific volume is V. And what this could be in the real case would be an application like, say, air being blown into a tank, or this could even be like air being put into the tire of a vehicle. Air is going in. The system boundary is the inside space of the tire in that case. And we ask that if this fluid element were to cross the system boundary, is there any work associated with this? Okay, so the question is, what is the work? Is there any heat? The answer is no, because we are saying that the temperature difference is not there, and to push this element we don't need heat, but we need to do work, which is a force which is pushing this element inside the control volume. So what is that force? In another way, what one can say is that we are looking at this whole thing as a system, that now our system is what we had drawn outside plus this little element. If this whole thing is looked at as a system, now we have fixed that mass. What is going to happen to this system is that as this fluid element goes in, this system boundary begins to disappear. It comes here, then it comes here, then it comes here, and finally it comes here. The mass of the system remained the same, but that little fluid element pushed in, which means that this system boundary was pushed in. So the final system will then look like this only. And whatever that little mass was, it went in somewhere over there. So effectively what we did that this system boundary which was here got displaced until it came over there. So this was the amount of displacement of the system boundary. And what was the force that caused this displacement? It was this pressure acting over this area. We say that the pressure is uniform over the area. So the force that pushed this was P times dA. And the displacement it did was dl. And we go back and say, what is our convention for work that we learnt in the previous module? We say that work is done on the system, that is negative. Work done by the system is positive. So with that, we get that the work done in this case, and we say this will be dW, elemental work done. This is this force with a minus sign because it is work done on the system. Force multiplied by the distance through which it went, dl. We are assuming that dl and A are normal, are in the same direction, are normal to each other. If the area had been like this and it was being pushed like this, the relation would have to be modified slightly. So that's the work required to be done by the surroundings on the system to push an elemental mass into the control volume. And we rearrange this, this becomes minus P times dA into dl. This is the volume of the element, and that we can write in terms of the specific volume. So this is minus P into small v into the mass of this element, delta M. So this becomes minus PV delta M. So although this work does not come in that work symbol that we used in the first, we'll use now W12 type of a thing, we have to accept that whenever there is a flow in, this much work is associated with the flow, and similarly if this fluid element were to be pushed out, the work associated with that would have been plus PV times delta M. And the work per unit mass, that would be dW by dm, this would be delta small w, this would be minus or plus as the case may be PV, and this is called flow work. So to get any fluid into a system, there is work associated with that, and to get a fluid out of the system, there is some work associated with that also. This is an important thing that we've got to keep in mind, and this particular type of a relation, this P into V combination, which is pressure into specific volume. Now remember, pressure and specific volume are both properties, so this will also be a property of the system. It will come back a little later when we look at the full statement of the first law. But this is an important thing. At first, we define mass flow rate. That's one thing now. And the second thing we have just done is define the case of flow work, which is work associated with the flow. So with that, we do the next step, which is write the conservation of mass. First for a control mass and then for a control volume. There are two things we will do. Now, why conservation of mass? This is the most fundamental conservation equation that every system has to obey. There is no question of violating this. It is always true, and so this is the first condition that a system has to specify before we can even talk about applying the first law of thermodynamics, the second law of thermodynamics, or second law of motion, or any other law. If this law is not satisfied, You just put the problem at that point and make sure that we have conservation of mass. Without that, there's no point talking about energy and entropy. That's how important this is. Okay, so for a control mass, our very definition was that we have a system boundary and a control mass is something that the system boundary is such that every molecule which is inside this system boundary always remains inside the system boundary. The system may change its shape, its size, that doesn't matter, but every molecule which was inside this has to be inside this. It doesn't have to be a single type of a molecule, it could be a mixture of two different types of molecules, it could be different phases of the substance, that's all okay. So once we say that every molecule inside the system has to be inside the system, the conservation of mass becomes very simple, that the mass in the control volume is constant. And this could be just a single substance, or it could be if there are two substances there, it could be the individual sum of masses, and then this has to be constant. There could be change of other properties, but the mass has to be constant. That's the thing. So there's nothing very unique or very tricky about the control mass issue. We now look at what happens to a control volume. And let's first see how we are going to frame the problem and then derive an equation. We'll do what we did a minute back, but with a slight difference. We say that here is a system. This is at time t1. Same system at time t2, with the difference being a very small time, delta t. So t2 is t1 plus delta t. And we said this is a system boundary which is a control volume which is fixed in space and its shape and size does not change. So this is our control volume. Same control volume in both cases. It doesn't change. And now we say that this has got a connection over there and a connection over there. So same thing will happen here. And what we say is that at time t1, we have this much mass in the control volume and this little element just adjacent to the control, the system boundary. This is about to go in, so we'll say that the mass of this is delta mi, which is wanting to go into the control volume. And now we say that this mass plus this mass, say the mass of the control volume, which was at time t, this is mCV at time t1. We define a control mass which is mCV t1 plus delta mi. So mass in this control volume plus this little element that was going to go inside, we take all of this together, say that this is the total mass and this is a control mass that we will track. Now if we track this control mass, what it would mean that after a little while t, when this system has gone down over there, this little elemental mass somewhere went and got inside this system. But we also give this flexibility that some other mass got out of the system. So we were tracking the control mass and we said when I push this, some little thing also came out over here. That's what we are basically saying, that the mass of this is delta M exiting delta ME. So the control mass changed its shape from being this, it became this. The total mass here and the total mass here is still the same. And now the mass at time t1, control mass, so mass in the control mass at time t1 was that much. And now we say that, well, at time t2, mass in the control volume, this will become mass in the control volume at time t2 plus what was going out, delta ME. Now this is the same control mass. That means this and this are equal. It is not necessary that MCVT1 is equal to MCVT2. This could be more than this or this could be less than this. Both are okay. And now we say that since these two have to be equal, what is, we put that as an equation. And it becomes MCV T1 plus delta Mi, which is the mass at time T1, is MCV T2 plus delta Me. So what this equation is telling us is that for that, this is mass in the control mass at T1, this is mass in the control mass at T2, which is T1 plus delta T. Now we do a small amount of arithmetic on this. We keep the delta Me term on one side. This becomes minus delta Mi plus MCV T2 minus MCV T1. This is equal to 0. And the next step, so this is the change in the mass in the control volume in time interval delta T. So what we do next is just divide everything by delta T, and we get that delta Me by delta T minus delta Mi by delta T plus this whole thing become d of delta T MCV. Change in mass in delta time T, this we can designate as delta MCV. And we say, look at the limit when delta T tends to 0, then this equation will become dme by dt minus dmi by dt plus ddt MCV is equal to 0. Now we look back what we just derived. This term and this term, they represent mass flow rates going into the system and going out of the system. This is the rate at which the control volume is changing its mass. This is a flow. This is a flow. This is not a flow. And that tells us how to write the next step of this equation. Then we get m dot E minus m dot I plus ddt mass in the control volume is equal to 0. So what it is telling us is that rate of outflow of mass, this is rate of inflow of mass, and this rate of accumulation of mass in control volume is equal to 0. And the 0 comes because you can think of this as rate of creation or destruction of mass, which in classical thermodynamics is 0. That is why the 0 was here. And so if we generalize this equation, we just have to put a summation that if the system had more than one inflows and outflows, say we have a tank into which from one pipe there is water coming in, there is a second pipe from which there is an inflow, there is another inflow there, and there is an outflow there and an outflow there, and this is our control volume. Then this would be inflow number 1, inflow number 2, inflow number 3, outflow number 1, outflow number 2. And to just make it unique numbers, we just call it 1, 2, 3, 4, 5. And that's what we learned in the first part of the course, that when you get a problem, first define what the system is, make the system boundary, identify all mass inflows and outflows. In this case, you got all these things coming in. Give state points. These are the state points that we define. And then now we have learned the first thing to do is apply the conservation of mass, which tells you that now we have more than one inflow. So all we will do is modify this equation a little bit and say that summation over all outflows m dot E minus summation over all inflows plus ddt of mcv is equal to 0, and that is our conservation of mass for the most general type of a problem. And its form that we have seen here, outflow rate minus inflow rate plus rate of accumulation in the control volume is 0. This type of a relation is true for everything. The second law of motion for a control volume will become, instead of mass, it will become momentum. For the first law of thermodynamics, instead of mass, it will become energy. So this becomes a very robust definition of a conservation equation for a control volume. And it's not just that we are looking at these type of problems, but if you are looking at, say, a reservoir of a dam, then same thing applies there, that the rate at which you have inflow into the reservoir minus the rate at which there is outflow is the rate at which the level of the reservoir goes up and down, how much water it accumulates or it's depleted. This also incidentally will apply to your bank account, where whatever money you had, outflow rate, which is what you withdraw, minus inflow, whatever comes in, is plus the rate of accumulation of money in your account, will be the rate of creation of money if you want interest or something like that. So this is a very, very fundamental equation, and there have been many industrial cases where the industry was having a lot of problems, and instead of worrying about energy and momentum and all those details, the problem got solved the moment we looked at conservation of mass and realized that something was not being accounted for. We accounted for that and things fell back in line. So this is a very, very basic equation that will always be there as your first starting point in analyzing any problem, especially when it's a control volume. Okay, so this is what is there in the part A of the notes that I have given out. There are a couple of changes you need to make there, because on page 2, you can see this. Here you need to make an important change. There's a mistake here. It is V cross. It is not actually a cross, but multiplied by dA. This should be replaced by a dot. It's a vector dot product and need not to be taken as a vector cross product. So this equation and the next two equations both are dot products. So please make that change. I will update the notes and put up a revised version on the forum. And then everything else has been derived the way before. And in the flow work, this is the inflow. This has to have a negative sign here. So in all these expressions, we have to put a minus sign, like I have done just now. So that's what we had discussed just now. So this part of the. Okay, so with that we've completed our formulation of the conservation of mass.